Our final presentation for this Engineering 4.0 session is by Brandon Westorp and Dave Meney of Vienna Engineering Services on innovative structural connections. So, gentlemen, over to you. Thank you.
Thanks, Nicolette. Welcome, everyone. Whether you're in a boardroom somewhere attending this conference or still sitting in your undies at home, we're hoping to impress you today with an innovative structural connection that, as the title suggests, contains no bolts or welds. So we're just going to briefly cover who we are and what the problem in mining construction is that we're dealing with, that we're addressing, what is altCONNECT, how it works, and then we're going to talk about the main section of this presentation, which is a structure test that we've done, and Brandon will present that, and then we'll discuss some limitations and our next steps. Finally, we'll just address who our target market should be. So who is Yenam? So we're an awesome structural engineering team. We design new structures and we rescue old ones from despair. So we do structural audits. We work mostly in the mining industry out of Perth, and we've been doing that since 1995. So what is the problem in mining construction? Well, in my opinion, I guess, the problem in mining construction is that we build everything with single sticks and bolt those together on site. So lots of transporting single items, lots of bolts, all individually erected. Site time costs a fortune in the northwest of Western Australia, and access is required to every connection, which increases the safety risk. So we all know about modular construction, which has been around for many, many years, and thank you, Joyce, for your presentation just a bit earlier on modular construction. It is the answer to a lot of those problems. It saves time on site, but it's got its own problems. So high transport costs for one. You're quite often shipping a lot of air. You've still got to join the units together, and we've seen that to be a problem. So you can bring pods to site, but then you've still got to climb up and join them all together with some sort of unique method. So we've come up with altCONNECT. altCONNECT is just like Lego for buildings. So we're talking about major components of structure, so partially modular, can be connected together without bolts and without welds. It's not really stick built, but it can be, and it's not really modular, but it can be. Whole buildings can be erected without scaffolding, so that kind of increases safety a lot. Platforms complete with services and equipment can be simply craned into position. We've got a little video for you to have a look at. So essentially we're talking about a spigot and a socket that fits together as the primary connection in the column of a steel structure. The rest of the structure, of course, being quite conventional steelwork. So this represents a structure that we designed and was constructed in 2015. So on the left is the traditional stick-built structure that was actually constructed, and on the right depicts a altCONNECT modified version of the system. And this video is just showing you how much quicker site erection can be using this methodology. So on the left is the traditional stick-built form. On the right is modular platforms being erected either off-site or on-site, and then simply craned into position over the top of the spigots. Apologies for the cheesy music. So it's kind of time accurate. So on the right, we're watching all the construction workers watching the traditional stick built going on and on and on in time. So we're talking about safety because most of that work is done on the ground. Speed of erection because most of it is just craned into position in modular elements. And better. There's better access around the structure without bracing. So how does it work? So in 2018, we actually presented in ASEC over in Adelaide, and myself and a couple of colleagues went through the presentation of the actual altCONNECT system, which is the spigot and the socket. So we did some test work and presented our findings on that. It was all very successful, and it gave us a impetus to continue forward. So how does it work? We need bending. So the connection will have any structure that has a lateral force with uplifting columns is also going to have associated bending, as long as it's not braced. So we rely on that bending to jam the connection and then resist the tension. So we demonstrated that in the laboratory with favourable success. And what we found, the secret was, obviously, if you've got enough bending moment, then you get enough resistance to tension. So we created this interaction curve, firstly in computer modelling, and then we validated it with the component testing in the laboratory. And we find that with that interaction curve, we can quite easily look at some results from a computer model and then choose the connection accordingly. So we did find some similarities, better than similar, I guess, between the model and the test work, which allowed us to validate the friction coefficient that we assumed in the model. So excited by all of that, we thought, well, if this is working as a single component, will it work in a whole structure? So that's our predicament. So we've developed a whole structure and did some modelling, computer modelling, and then we built a 1/6 scale of that, incorporating 12 of these altCONNECT connections. And then we tested it to failure at Curtin Laboratory earlier this year. Now, Brandon, my colleague, is going to continue with this presentation and share all that findings with you.
Thank you, Dave. So a little bit of our design process. First, we took the existing transfer tower and we simplified the model down a little bit for our test. We then scaled it from a 6 by 6 metre plan at 13 metres height down to a 1 by 1 metre plan at 2.275 metres height, so a 1:6 scale. We introduced the connections to the beam and column interfaces using moment end plate connections. And these end plate connections provide us with a tolerance in the structure where we can use shim packs to adjust. So our test structure assembly, the base columns were bolted to transfer plates. They're those big plates at the bottom here. And they were designed to adapt our structure to the university lab's strong floor in place of a conventional concrete footing. We wanted to make sure that when we designed them, the transfer plates wouldn't be the things that failed. So then we assembled the floors separately on the ground and bolt the sockets to the end plate connections. We then inserted shim packs to adjust the tolerance and keep the column centers correct. Then each floor is lifted and placed onto the columns below. The tapered head of our spigot allows for an easy location onto into the sockets. So each floor just drops into place. Then the next set of columns can be installed and the process is repeated. Finally, the top floor is installed and the assembly is complete. Each floor was checked to be level and that the columns are plumb, and we had a perfect installation. Once assembled, we then put our testing equipment in place. We were using LVDTs to measure displacement, both local and global. And then we also used them to measure our connection separation and slip. We had strain gauges on the spigots of each connection to monitor for stresses and strains during testing. And the lateral load was provided at the top floor via a hydraulic jack with a load cell so that we can measure the force applied. So did it work? Of course it did. So the connections held firm during the lateral load tests and they didn't yield. But we were confident of that, that the scaled test structure would work before we even built it and took it to Curtin University. The test provided us with information that we can feed back directly into our models and improve their accuracy. So the connection capacity of altCONNECT that we tested. So during our tests, we first reached a lateral load of 10 kilonewtons. which was applied at the top of the structure, and we had zero yielding. The structure remained completely elastic and returned back to zero. Then we reached 20 kilonewtons of lateral load with no yielding in the altCONNECT connections at all. But it's important to note that the 20 kilonewtons was actually 70% higher than the predicted ultimate lateral load from our structure design. So we predicted that below that 20 kilonewtons, we would have yielding in the column base first. So that was expected, and that happened during testing. But that was an expected result as we took it well past the ultimate lateral load. So our slip in our friction connection. So our altCONNECT connections had a clearance between the two components of 0.1 millimeters. There was minimal slip during this test, with 30% of that slip occurring during the first 2 kilonewtons of load, or the first 10% of our loading. At a serviceability load, we had a serviceability load of 7 kilonewtons, and the maximum slip was only about 2 millimeters. So for our deflection, 24% of our deflection happened during those first 2 kilonewtons of loading. And that indicates to us that the slip is responsible for a decent portion of the deflection as it occurs during the initial take-up of that clearance or the slack in the connections. In a full-scale structure, this wouldn't scale linearly, as the clearance won't be scaled up by 600% to make the one-to-one structure like the geometry would be. So for serviceability, as I said before, our lateral load is 7 kilonewtons, and that had a resulting top floor deflection in our test of 35 millimeters. Also discussed before, the partial contribution to that deflection is due to the slip seen in the connections. From our modeling, our expected deflection under that service load was 19 millimeters, but with some calculations, in a full-size scale connection, that internal rotation won't be quite as bad inside the connection. It actually reduces by a factor of 6 when we have a full-size connection. So if we calculate that backwards, we get an estimated deflection of 23 millimeters. So the stability of our connections. In our structure, the connections had a maximum slip of 3.5 millimeters during the 20 kilonewton load test, and they returned to 0 when when the load was removed from the structure. So we only had self-weight and lateral load for bending. So that's probably the worst case scenario, as we have the most uplift. But the bending was enough to engage the connections in that friction lock and resist the connection separation. So in a real structure, the addition of floor plates, more secondary members, equipment and machinery would actually add more dead load to the structure and increase that bending moment, which is critical in maintaining a strong connection when lateral loads are present. So the strength of our connections during our testing, we only reached 70% of their capacity, so they remained completely elastic in nature during our test. Yielding occurred at the base of the columns, which was predicted, and that happened at a load of 20 kilonewtons, which was 70% larger than the ultimate design load. Our altCONNECT connections were also designed for that ultimate design load, but we didn't have any yielding or slip at the 20 kilonewtons, so they survived the 70% larger load. So our limitations and recommendations, the connections still plan to be tested for cyclic and vibration loading, using the same current clearance of 0.1 millimeters annually in the connection. Cyclic loads such as the seismic test are expected to be favorable with that sort of tolerance. And we're also going to be working further towards environmental factors such as moisture, dirt, and corrosion in the connection, as that will help us understand their impact on the connection's performance and design life. And lastly, our target market. The concept has initially been designed for the mining industry, where the high cost of labour on remote sites demands speed efficiencies to improve. Typically, the type of structures it would be suited for is conveyor transfer towers and take-up structures, stair towers, and the like. However, any moment-resisting steel structure is fair game for altCONNECT. So thank you for listening to our presentation, and we'll take some questions.
Thank you so much, David and Brandon. The paper on your structural altCONNECT connection was insightful, and I'm sure it will be adopted industry-wide in no time. We have a question from the audience. Under earthquake loading where the forces are sudden and instantaneous, how do you believe this will perform in high earthquake zones such as New Zealand, Japan, etc.?
Yeah, it's a great question. It is, as Brandon just pointed out there, with limitations and next steps, it is definitely on our radar to test the performance of an altCONNECT structure in a seismic environment or in a vibration environment. So granted, the connections aren't joined with bolts or welds, so you could imagine that there's potential for those to jump. But when you think about it, the structure isn't actually bolted or welded to the ground either. So this is really just a stability issue. Our connections are not unlike any that we have actually in real life where we're just relying on friction. So we hope that what would happen in an earthquake is that the structure responds quite ductilely and bounces back. So we found under static loading that even though there was a little bit of slip in the connections, everything came back to normal. There was only a couple of mils of movement. A bolted structure, of course, push to yield is going to also move because we've got a couple of mils of hole clearance for our bolts to slip in. So yeah, as I say, we're excited to see those results. We will do some more testing in that, but we expect that we expect it to be quite favourable.
Thank you so much. Let me see if I can find another question. There's another question from the audience regarding uplift. Would there be benefit in adding a cross bolt to positively connect rather than relying only on friction? And this comes from Andrew Morrison.
Yeah, thanks, Andrew. So I guess the answer is, why would you do that? If you had a connection that worked without bolts or welds, why would you put a bolt or a weld in there? Unless you were trying to address the issue of serviceability with movement. I mean, this, you know, a steel moment resisting frame that's glazed wouldn't really be a target market for us here, because we wouldn't want building movement such that it cracked glass. But we have looked at the structure in the laboratory and wondered, how could we make this more rigid? And putting a grub screw concept or a grub bolt into the connection would be quite doable, and we would consider doing that. We wouldn't consider making that a mandatory part of the connection, however, because one of the benefits of this system is that you don't have to be at every connection. So, you know, we want to avoid the cherry picker. We want to avoid all of the scaffolding. We simply want to be able to stack these platforms one on top of the other, crane in a stair tower, and walk up to the levels. So if you can do that, and you can get to those connections once you're on those grated floors with hand railing and safety, then why not bolts and braces? But don't forget also, we're in engineering 4.0. We're changing the status quo of engineering here. So, you know, we're used to bolting, we're used to welding, even in the home building industry, we're used to using plywood panels with glue on them, and then for God's sake we're putting a nail every 100 mils or something through them just because the glue might not work, even though the manufacturer says the glue will work for 30 years. So we've got to start thinking about you know, things a little bit differently, and that's what we're pushing here at ASEC.
Yes, that's true, and your product will certainly be a game changer in the industry, and I think the only way is up. So thanks again for your insightful presentation. I will relay back to Nicolette Cambo to provide closing statements.
Thank you.